Hi everyone, this is topic 5.3 concentration changes over time, and this is taken from AP Chemistry College Board. In this topic I'll be talking about the rate law and how can we actually find the integrated rate law, and from that integrated rate law how can we actually plot a graph between the concentration and time, and if you are given a graph between concentration and time, how can you find that what order will it be. So let's start. I have already mentioned this in topic 5.1 that what is the meaning of reaction rate. So reaction rate is basically the speed with which the reaction is happening. And as it says speed means something is happening with respect to time. So that's why here also I would say that the reaction rate is a change in the concentration of a reactant or a product with time. And the unit of the reaction rate is molar per second. Now here the A is the reactant and B is a product, and here you can see it with respect to time that how the reactant, that is A, is changing into B. When we are writing the rate of this kind of reaction, we write it in the form of rate is equal to minus delta A over delta T, and we can also write it in terms of products where rate is equal to delta B over delta T, where delta is basically the change. When we are talking about delta A, that is change in the concentration of A, and this is change in the concentration of B with respect to change in the time. Now here you can see that there is a difference of this negative and there is no negative here in the second equation. Now why is it so? That because in the first equation we are talking in terms of reactants, and reactant, as the reactant is being used up, so that's why it is minus here, and B is the product which is being formed, so that's why there is no negative sign here. Now when we see this graph, you can see that it's number of molecules with respect to time. You can also write it as concentration of A or B with respect to time. Now when we are talking about A, I told you that A is changing into B. It means the number of molecules of A is basically decreasing, and this is how the graph will look like. It is not a straight curve, but it will first go down faster, but with time it will start becoming constant. And same is the case with B, that is B is a product, so that's why the number of molecules of B will basically increase, and this is how the graph will look like, that initially it will be a steep curve, but with time the slope will actually decrease. So this is the concentration versus time curve for any reaction. Now, when we are talking about the order is what we get from the experiments. Now, order tells you that what is the speed at which the reactant is basically being consumed. Now, if we talk about the differential rate law, it is the same what we did just now, that rate is equal to minus delta A over delta T. But here we are talking about the zeroth order. Zeroth order means that the rate of the reaction doesn't depend on the reactant concentration. So we have just written K here, that the small k is the rate constant. If you want to know more about the rate law, you can watch the topic 5.2. And for the first order, it will be again rate is equal to minus delta A over delta T is equal to K multiplied by concentration of A raised to the power 1. Why 1? Because it's the first order reaction, and the second order Y, it will be written as rate is equal to minus delta A over delta T is equal to K, that is again the rate constant, times the concentration of A square. Now square tells you that this reaction is second order with respect to A. Now when we are plotting the curve of concentration with time for the zeroth order, it will look like this. That is, initially it will be a steep curve, and suddenly it will become constant. Why? Because it is not depending on the concentration of the reactant. And when we are talking about the first order reaction, it is depending on the concentration of A. That's why initially it will be steeper, but it will become constant with time. The slope will actually decrease with time. And for the second order, it will be more steeper. Why? Because it's second order. It means that it's consumed more and more faster, and that's why it will be steeper, but again with time the slope will decrease. Now when we are writing the integrated rate law, integrated means we have done some integration in this equation, and when we do the integrated rate law for zeroth order, it is concentration of A is equal to initial concentration of A minus KT. Whenever the 0 is written at the subscript, it shows that this is the initial concentration. And for the first order, it will be ln A is equal to ln A naught minus KT, where ln is the natural log. And for the second order, it will be 1 upon A is equal to 1 upon A naught plus KT. You need to remember these integrated rate laws. Now, when we are plotting the curve between concentration and time here, that is A versus time here, this slope will actually give you the minus K, that is minus of rate constant. And if the curve is between ln of concentration versus time, it will be again straight line here, and the slope will be minus k. Now these things we have got from these integrated rate law equations, because we have made t as x-axis and a as y-axis, and that's why the slope is minus k. If you remember the equation of line, that is y is equal to mx plus c, from there you get to know that why the slope is minus k here. Now when we are doing the plot between ln of concentration versus time, it will again the slope will be minus k, and here we are doing the plot between 1 upon concentration versus time, the slope will be positive and it is equal to k. Why? Because here the sign is plus kt. So if you are given these types of graphs, from here you can get to know that what order is the reaction. Suppose if you are given a graph between ln concentration versus time and it is a linear curve, so from there you can get to know that the reaction is first order with respect to that reactant. Radioactive decay processes provide an important illustration of first order kinetics. So whenever we are talking about the radioactive decay processes, they are mostly the first order reactions. Let me tell you what is the meaning of T half. T half is basically the half-life of that reactant. Half-life means how much time it has taken to become half of what we had started with. So for any first order reaction, T half will be equal to 0.693 upon K, where small k is the rate constant and T half is the half-life of that reactant. A higher initial concentration has no impact on the time needed for half of the reactant to be consumed. If you are starting with more of the concentration, then also the T half will remain same, and if you have started with the lesser amount, then also the T half will remain same. So here I want to tell you that the half-life will not depend on the initial concentration of the reactant. The question here is that the radioactive decay is a first order kinetic process, and carbon-14 is a radioactive and often used for radiometric dating as it decays to nitrogen-14 via the following beta decay process with a half-life of 5700 years. So this is the equation which is given for the radioactive decay of carbon-14, where it's changing to nitrogen-14 and with a beta decay. Now the question is, what is the rate constant for the process? Now the information which is given to you is only the half-life of this radioactive decay, and they have told you that this decay is first order kinetic process, and they have given the options and you have to select which one is the correct option. Now here you have to apply the same equation, that is small k is equal to 0.693 upon T half, where T half is the half-life and small k is the rate constant. So you will put the value here, that is 0.693 upon 5700 year, and from here you will get the answer that 1.2 multiplied by 10 to the power minus 4 year inverse. This is the rate constant for this process where you are given the half-life, that is 5700 years. So with this, I finished this topic, that is how the concentration is changing with time for different order reactions. And the thing which you need to keep in mind here is that if you are given a graph, that how do you get to know that what type of order reaction it is. And if you are given the radioactive decay question, then if you will be asked to either calculate the rate constant or the half-life of that decay. I hope this topic is clear to you, and if you like the video, then please subscribe to my channel Log IOTA and press the bell icon.